Next we see the notion of a unitary transformation, and the definition is this: V as usual is your finite dimensional inner product space, and A of V is the operator algebra of all operators on V. An operator T on V will be called unitary if the inner product of any two vectors u and v coming from the space equals the inner product of their images under T, ut, vt. And that is why a unitary transformation preserves all the structure of the space V, its addition and its multiplication by scalars, which anyway are preserved by any linear transformation. But a unitary transformation additionally also preserves inner product, and as a consequence it also preserves length. You take any vector from the space, then its length by definition is this, the square root of its inner product with itself. This, however, is equal to this by the definition, and which equals the length of Vt. So applying a unitary transformation to any vector in an inner product space preserves its length, it does not change its length. Next we have lemma 6.10.2, which gives us a sufficient condition for unitarity of an operator. If this happens, if the inner product of Vt with itself equals the inner product of V with itself for any vector V in V, then also T is unitary. You recall the definition that we saw just now. If ut, vt is equal to u, v, then T is called unitary. So this is requiring less, but even then, if this is true, then T will be unitary. Let's prove it now. The proof starts like this. It will remind you of the previous proof that we saw in the previous video of another result. So we start by taking any two vectors u and v in V, and then using what is given to us, this is what we write. We apply this condition on the vector u plus v. So the inner product of u plus v t, that means the t image of u plus v and itself, equals the inner product of u plus v and itself. And then first we apply the fact that t respects addition. So this becomes ut plus vt, and that one also the same thing is ut plus vt. And we expand the right hand side using the definition of inner product, its linearity, conjugate linearity, all those things. And that way we get this u, plus u, v plus v, u plus v, v. And then we do a similar thing on the left hand side. That way we get ut, plus ut, vt plus vt, ut plus vt, vt. And the right hand side is just this. And let's now continue. So in the next line we write in place of ut, u, u, again by the given condition. And in place of vt, vt, we write v, v. These two middle terms stay as they are. And the right hand side for now, it just stays like that. But then you can cancel this u, u from both sides and also v, v from both sides. And that way you get this boxed equation. The inner product of ut and vt plus the inner product of vt and ut equals the inner product of u and v plus the inner product of v and u. So next part we do, we replace in this equation v with iv, where I is your imaginary unit. You can do that for two reasons. First is that your underlying field is the field of complex numbers, so I is available, and the second thing is that this equation is true for any u and v. So that's why in place of v you can use iv. Now what do we get if we do that? Let us first carefully put iv in place of v. ut, ivt, using brackets here because t is being applied on iv, that is why, to emphasize that fact. Similarly, plus ivt, ut equals u, iv plus iv, u. Alright. Now then in the next line, on the left hand side, first I comes out and you get I times vt here. The difference between this and this of course is clear to you. This is the t image of the vector iv and this is I times the t image of v. and we are able to write this one in place of this one because T is a linear transformation, so it preserves scalar multiplication, that is why. Similarly here also I comes out and you have Vt comma Ut. What is happening on the right hand side? If you try to take I outside from this second coordinate, due to conjugate linearity, its complex conjugate will come out, which is minus I here, I mean. So that's why you have minus I here. Whereas from here if you take I outside, then that just follows ordinary linearity, and that's why simply I comes out. A similar thing happens in the next line with the left hand side. We want to take I outside of this inner product, so its conjugate comes out because it's coming out from the second coordinate. So you have minus I here, minus I times Ut comma Vt, but from this one just I comes out. I times Vt comma Ut plus I times Vt comma Ut equals minus I times U comma V plus I times V comma U. Now of course you can cancel I from both sides. Doing that you get this other boxed equation. Minus of Ut comma Vt plus Vt comma Ut equals minus of U comma V plus V comma U. Now if we add these two boxed equations, then these two will cancel each other and these two will cancel each other. These are however the same, so twice those quantities will appear, and then let's see what happens. So I decided to keep this part, okay, did not erase it so that you can see. So on the left hand side, after you do the addition, did not actually also write much. You understand that we are adding this one and this one because of lack of space. These two terms cancel each other because they are minuses of each other. You get twice of this, 2 times Vt comma Ut, that is equal to, again these two cancel each other, and on the right hand side you get 2 times V comma U, and then you cancel 2 from both sides, which you can do because 2 is non-zero, and that way you get the inner product of Vt and Ut equals the inner product of V and U, and that is why by definition T is unitary. So starting from the hypothesis that the inner product of Vt and itself equals the inner product of V and itself, we have been able to actually recover the definition. So this is where the proof ends.